So hello everyone. In today's class, we'll derive the element stiffness matrix for beam element. So in the last class, we have derived the shape functions for beam element in terms of natural coordinates and in terms of global coordinates. In terms of natural coordinates, if you derive them, we call them as Hermite shape functions. So we can use either global coordinate shape functions or natural coordinate shape functions in order to derive the stiffness matrix for beam element. As we all know, so beam element has how many degrees of freedom per node? 2 degrees of freedom, 2 degrees of freedom per node. So for a single element, so total there are 4 degrees of freedom. So from this we'll come to know that so our stiffness matrix, element stiffness matrix for beam element should be of 4 cross 4 matrix. 4 cross 4 matrix. Now let us consider a beam subjected to bending moment M, length of element BLE. Okay. If you are considering the global coordinates, when you apply the limits after when you are integrating it, so the limits when you are using global coordinates will be 0 to LE, but when you are using natural coordinates, it will be +1 to -1. Okay, xi will vary from +1 to -1. Let dx be the small element in the beam and dA be the cross-sectional area of a beam. So in general, strain energy stored in a beam is given by half integration with respect to volume sigma into epsilon. Let me call this as expression 1. Now our aim is to find what is sigma, what is strain for a beam. So strain for beam in y direction is given by epsilon equal to -y d square v by dx square, where v is nothing but transverse displacement. We know there are 2 degrees of freedom, one is transverse displacement and slope theta. Okay? Degrees of freedom per node. So v is nothing but transverse displacement. So this is the strain in y direction for a beam. So how did you get this strain as -y d square by v by dx square? So we know the bending moment equation for beam is given by -ei d square y by dx square. So rearranging this, taking this I on this side, so we'll get this expression from bending moment equation. We know m by I equal to sigma by y. So substituting in place of m by I, sigma by y, we'll get this expression. So don't get confused between this y and this y here. So here this y is nothing but your transverse displacement v, and this y is farthest distance from neutral axis. Okay, we denote it as y or c. Okay, now taking y on this side and e on this side, so this is what you get. So from Hooke's law we know strain is directly proportional to strain. So strain is given by sigma by e. Okay, is it? So this sigma by e is nothing but -y d square v by dx square. That is what is the strain in y direction for beam. Okay. If I take this e on this side, so that is nothing but your stress in the element for a beam. Let me call this as equation A and this is equation B. So when you substitute these two equations in equation 1, this is what you get. Okay. Now, and the limits, since we have dx here, so with respect to dx, what are the limits? 0 to LE. Okay. So dv is given by dA into dx, which is nothing but volume of an element. Okay, so which will be dv. So y square, integration of y square into dA is nothing but your moment of inertia r. So this is your strain energy for a beam element. This is nothing but the strain energy of a beam element. So let me call this as equation B. Now our interest is to find out what is this d square v by dx square. Now in order to find this, we know from our previous derivation v equal to your displacement v equal to n into q. where n is the shape function matrix and q is the displacement matrix. When you differentiate this equation with respect to x twice, this is what you get, b into q. So where b is called as strain displacement matrix. Similarly, we had a strain displacement matrix for a 1D bar element, which is nothing but 1 upon Le minus 1, 1. These equations we have used it while solving the problems as well. Okay, we'll see what exactly is b in the next slide. Okay, now substitute this d square v by dx square in this equation. So substitute here. So this is this is what you get here. So when you split this b into q whole square, we know these b and q are in terms of matrix. We cannot write b into b, q into q. Okay, so we are violating the matrix property. Okay, so if a and b are two matrices, if we take the square of those two matrices, it will be written as b transpose a into b. Then only a into b whole square will be equal to this term. So writing it, applying this condition, so this will be equal to q transpose b into q, and remaining terms we're writing it as it is. Let me call this is equation 3. Okay, so next, strain energy stored for general 1D element is given by. So for general strain energy equation, we know it as half of kx square. If I take x as q and write it in matrix form, this is how you write it. We have already used this expression in the previous derivations. So half q transpose k into q. Let me call this is equation 4. So when you compare these two equations, equation 3 and equation 4, when you compare that, you get k as integration of ei integration of 0 to le b transpose into b into dx, where k is nothing but your stiffness matrix. We are interested in obtaining the expression for this. Okay, so this is what you get, k equal to ei integration 0 to le b transpose into b into dx. Let me call this as equation 5. We can directly use global coordinate shape functions and for b and b transpose, then obtain the expression for stiffness matrix k. So but using those terms, it will become tedious. So in order to make the simplification easier, we'll use natural coordinate shape functions, that is Hermite shape functions. So we'll convert this dx in terms of d xi, and when you convert this from global coordinate to natural coordinate, so the limits will change from 0 to le to -1 to +1. Okay, so we know from relationship between natural coordinate and global coordinate, we have dx equal to le by 2 d xi. When you substitute this here, this is what is the expression you will be getting: ei integration -1 to +1 b transpose b le by 2 into d zeta. Sorry, not d zeta, it is d xi. Okay, so rearranging it, let me take 2 on this side and le is here. Now this is what is b. Okay, here in the previous case I told you, I have not told you what is b. So when you differentiate this term, this is what you get, okay, b as. Okay, so it is nothing but dou square n by dou x square. Okay, but what is n? It is n1 n2 n3 and n4. Okay, so this is in terms of global coordinate. This is your strain displacement matrix for beam element in terms of global coordinates. We have to convert this in terms of natural coordinates, and this is the expression you'll get. So first we'll see what are n1 n2 and n3 and n4 which you have derived. So this is your n1, which is equal to h1. This is your n2, which is equal to le by 2 h2. Okay, and this is your n3, this is n4, which is equal to le by 2 h4. So differentiating each of these terms, okay, so before differentiating each of these terms with respect to xi, we have to convert this first in terms of d xi. Again we'll apply chain rule, dou n upon dou x equal to dou n upon dou xi into dou xi upon dou x. So from this relation we can write dou xi upon dou x as 2 by le. So what will, again squaring this term now, so this is what you get, dou square n by dou x square as dou square n by dou xi square into 4le square. So 4le square will be there in each of these terms. Each of these terms there will be 4le square. So when you take 4le square common outside, so this is what it remains: dou square n1 upon dou xi square, dou square n2 upon dou xi square, dou square n3 upon dou xi square, and dou square n4 upon dou xi square. Okay, let me call this equation 7. Now we have to obtain the values for these by differentiating twice these each of n1, n2, n3 and n4 terms. So individually one by one we have to do it. So this is the expression n1. What is n1 here? This is n1. Okay, so when you integrate, differentiate it with respect to xi once, you'll get this. Okay, 1 by 4 as it is. Differentiation of 2 is 0. Then minus 3 xi, it is minus 3. Then 3 xi square. Again differentiate this with respect to xi. You will get 6 xi by 4. Yes, dou square n1 by dou xi square. Then similarly you do it for dou square n2 by dou xi square. This is n2. Differentiate it once, you will get this term. When you differentiate it again, this is what you get. Okay, so taking 2 out common, this is what you get: le by 4 minus 1 plus 3 xi. Okay, then next is dou square n3 by dou xi square. So this is your n3. So differentiate it once, you'll be getting this. When you differentiate it twice, this is what you get: minus 6 xi by 4. Similarly you do it for n4. This is the expression what you'll be getting. Now substitute all those in this expression now, equation 7. When you substitute them in all those equations, this is your strain displacement matrix for beam element. Now when you see this equation, we want B transpose as well. We got B. Now what is B transpose? Okay, this is your B, right? I've taken 4 common here, and this is the expression for B. When you take B transpose, this is B transpose. Next we have to multiply B transpose into B. So multiply B transpose into B. Don't forget to write 1 upon le square. Okay, so 1 upon le square, 6 xi le minus 1 plus 3 xi minus 6 xi le 1 plus 3 xi, and same will be here. Okay, this is your B transpose, this is your B. So go on multiplying this. When you multiply this with respect to each of the term in this matrix, you'll be getting first row. This again with these all, you'll be getting second row, and this with this, each of the term you'll be getting third row, and lastly this with this you'll be getting, and here outside 1 upon le raised to 4. Make sure you multiply it carefully. You can see here, I'll just tell 1 or 2. 6 into 6, 6 xi into 6 xi, 36 xi square. Then 6 xi into this one, it is 6 xi le minus 1 plus 3 xi. This into this minus 36 xi square. And this into this 6 xi 1 plus 3 xi. I'll tell you these terms. So this will be this multiplied by this one. So le square, that is le square. Then so both the terms are same, that is minus 1 plus 3 xi whole square. Okay, and I'll tell you what is this term. That is this multiplied by this one. So you can see here it is a minus b, it is a plus b, where a is 3 xi and b is minus 1. So when a plus b, a minus b is nothing but a square minus b square. That is what is applied here. Okay, so on, go on multiplying this, and this is what the matrix you'll be getting, which is nothing but 4 cross 4 matrix. Now our duty will not get over here. This is not the stiffness matrix of beam. So this is actually the stiffness matrix. So we have just got B transpose into B. Now our next step is to integrate each of these terms in the matrix. To make the integration simple, okay, so integrating all these 16 terms in the matrix becomes tedious. Okay, so in order to make the integration simple. There will be three terms. Okay, there will be three integrations only. So integration of 1 into d xi, then integration of xi d xi, then integration of xi d square. Okay, from limits +1 to -1. So when you multiply these terms, you can see only xi square, xi term and a constant term. So integration of constant xi and xi square. Okay, if you integrate those, it's more than enough. So when you integrate constant term, so this is what you'll be getting. If you integrate 1 d xi with respect to limits, xi, if you apply the limits, -1, -1, -1 here, it will be 2. Okay. Then when you integrate xi d xi, so when you integrate xi square by 2, when you apply the limits, half half, so it will become 0. Okay. And when you integrate xi square, it will be xi cube by 3. When you apply the limits, 1 by 3 minus 1 by 3, it will be 2 by 3. Okay, 2 by 3. Now the integration of whole this one, when you integrate it, so before integrating, I have just split the terms which are in brackets. I have factorized it. So I multiplied each of these terms inside here. So this is the expression you will be getting. So 36 xi square minus 36 xi 6e, sorry, minus 6 xi le plus 18 xi square le. So go on multiplying this and write the terms. So you can see 36 xi square, when you multiply here, minus 6 xi le plus 18 xi square le. Okay, you can see here. Go on multiplying and write the terms. Now in place of wherever you have xi square, you substitute 2 by 3. Wherever you have xi, you substitute 0. Wherever you have constant term, like here, you substitute 2. Substitute 2. When you do this, you can see here each of the terms is there. Wherever you have xi square here, so here there is xi square, here there is xi square, here there is xi square. In almost all the terms you have xi square. And here you have constant term, that is constant here. Then this is xi here. In place of xi it is 0. I'm just telling you few terms. Okay, just go through all these. Okay? So when you substitute this, when you simplify this, you can see 2 by 3, 36 into 2 is 72, 72 by 3 is 24. So here 18 into 2, 36, 36 by 3 is 12, there is LE, so 12 LE. So on, go on doing it. This is the expression for integration of -1 to +1 B transpose into B into dxi. Next we are interested in this K equal to EI by 2 integration B transpose B into dxi into LE. Substitute this in this expression. 1 LE will get cancelled out, you will remain with this. 2 will get inside the matrix and you will be remaining with half of this matrix over here and EI as it is. So this is your stiffness matrix of beam element, which will be used to solve problems. So it is very easy to remember. So EI by LE cube will be there, as it was EA by L in case of trusses and bars. Here it is EI. Okay, here I is moment of inertia, E is the Young's modulus, and L is the length of the element. EI by LE cube, so 12, 6 LE, minus 12, 6 LE, 6 LE, 4 LE square, minus 6 LE, 2 LE square, minus 12, minus 6 LE, 12, minus 6 LE, 6 LE, 2 LE square, minus 6 LE, 4 LE square. Okay, just remember these first 4 terms. Same thing you write it here, but instead of 4 LE, you write it 2 LE square here, and these two will be minus, and this will be same. This 4 terms and this 4 terms. And since the stiffness matrix property, it is stiffness matrix is always symmetric. Okay, so these and this will be same, and this are same, but these two will be minus. It's very easy to remember. So this is the expression for stiffness matrix of beam element. Okay, we will be using this to solve the problems. Thank you.